Hi, everyone, and welcome to the MLOps Live webinar series. My name is Sahar, and I'm Iguazio's VP Marketing, and it's great to have you all with us today. This series of webcasts is all about operationalizing machine learning and bringing data science into real business applications. And today, we're going to be discussing a topic that is of great interest to us all and is really more relevant now than ever: how to deploy data science at scale in an efficient and effective way, or more simply, how to save costs and accelerate time to market. Because in today's economy, we all understand the significance of cost savings and of seeing the business impact of our AI applications and seeing them quickly. To guide us through these topics, we're delighted to have Jason Evans here with us today. Jason is the Director of DXP Innovation at Quadient, a leading provider of omnichannel customer experience solutions. Quadient delivers 8 billion personalized experiences annually, and its solutions make it possible for hundreds of thousands of businesses to continuously achieve customer experience excellence by automatically creating and delivering meaningful interactions consistently across all channels. And Jason is going to tell us all about how he and his team leverage data science at scale for these use cases, and how he built his AI pipeline and workflows to save costs and slash time to market. Also with us is Yaron Haviv, Iguazio's co-founder and CTO. Yaron is a serial entrepreneur and served in multiple CTO roles before starting Iguazio in 2014. He will start us off with a quick intro to MLOps, and later in the session, he'll speak about leveraging ML pipeline automation to reduce time and resource consumption. He will demonstrate this with a live demo of open source technology. At the end, as always, we'll have time to answer your questions, so do write those in the Q&A panel at the bottom of your screen, and we'll try our best to address them all. We've put everyone on mute, and the session will be recorded and sent to you afterwards, so no need to worry about recording. And I will now pass the mouse virtually over to Yaron to kick things off.
Okay, thanks, Sar, and welcome everyone to this episode. So before going into Jason's presentation, and he has a lot to say in that area, let's first understand what is MLOps, what is the problem that we're trying to solve. So most of the efforts today in data science are still focusing on the experimental stage, taking some small data sets, CSV, Excel spreadsheets, feeding them through notebooks and Jupyter into some algorithms, generating results, in some cases using automation tools, cleaning the data and running some AutoML tools and generating a model. But once you've done that, the real thing that you want to do is plug this into a real application. In real applications, you have live data that may come from various sources. Some of those will be real-time, like streaming. Some of those will be operational databases or APIs that we have to hook into. We have to go and process data at scale, not something we do on a notebook in memory. And then we have to automate the training, because one of the things that we constantly see is potentially model drift because of data changing, especially in this environment. Models and code may change, so we have to retrain our models periodically based on detection of various events like code change or drift, etc. And once we've created models, we have to serve those. And model serving has to be elastic to fit different scales. The model serving aspect has to also be able to monitor itself, monitor the drift, be able to move, change versions in a rolling upgrade, allow canaries. Some of those things we're going to see in the demo later in the presentation. And one of the most important things, it also needs to work with live data when you're doing the serving. So the process of moving from the research and experimental stage where you generate a model, and this model may be low performing and potentially, let's move to the next slide, sorry. Okay. So once you've developed your code, which may consist of a model or some glue logic or some data engineering code, you have to go through a long process of operationalizing that. You have to package it usually in containers and builds and scripts and conduct local testing, and then you have to scale it out to meet the demand. You may find out that the performance is not adequate, and the latency is not what you need to achieve, or the number of transactions is below what you need for your application. So then you're starting to apply caching and parallelism and integration with GPUs and other things. And before you go into production, everything has to be able to be observed in production. You need logging, you need monitoring, you have to safeguard your data with security policies, you have to apply versioning to almost everything, data, code, and executions and experiments. And finally, you have to automate the process, so when there is a change in code, a change in data, or a change in an event like drifting of a model or other aspects, you have to automatically rebuild. You don't want to do this manually. We see that companies that do manual processes eventually take very long time to get to production. And this is what you'll see, that in Jason's presentation, most of the focus is around automation. This is how they can achieve this huge agility and lower cost and scale and higher scale as they do. So just moving to the next slide, we need to think of machine learning and MLOps as sort of a continuous flow. A continuous flow where you're feeding data from various sources on one end, you apply data preparation and analytics, and essentially denormalize the data and form this data ready for serving or training. Then you need to train, and then sometimes apply multiple strategies to training, multiple parameters, multiple algorithms, and choose the best solution. Finally, you need to deploy those models and attach them to APIs. So that is essentially a continuous workflow that needs to be automated using MLOps technologies. So with that introduction, let's move to Jason's presentation, where he's actually going to show us how they're doing it at Quadient.
Thank you, Yaron. It's great. It's great to meet everybody virtually and be here today. So let's kick it off. I'll go to the first slide. So innovation that accelerates digital transformation is really hard. And we always ask ourselves a lot of questions, and we validate those questions to determine if what we're building is going to be an improvement or it's going to be truly disruptive innovation. So some of those questions are obviously difficult, and we have to validate the results every step of the way. And most software is built like a roadmap where the routes and destinations are established well before we actually write any code. But what if we could build software like a compass where the outcomes weren't predetermined, so that every user could have a unique experience tailored to them every time they use it? Where we push past this hello customer or hello platinum customer to hello Jason or hello you. Becoming fluent in a customer of one is, it basically does require that that the experience be hyper relevant, hyper personal, driven by context. And it's the only way that we can ever truly keep pace with the speed of customer expectation and innovation. So from our perspective, we wanted to build such a piece of software to determine whether or not it would continuously impact the availability of these experiences for enterprises and their customers. So our platform essentially overlays enterprise existing infrastructure and current investments. And I know it may sound corny, but I sort of see it as a bridge over troubled silos. Everybody needs to laugh a little bit. And we want to ensure that at every interaction, it's not predetermined. We are learning every step of the way. So every time a piece of data change, every time anything changes, that experience is unique to the individual who's interacting, regardless of digital channel. So we figured out what we wanted to build. We understood that it wasn't going to be easy. We determined that we would need tons of data sets. We would need infrastructure. We would need to figure out exactly how best to deploy it. So we made an early choice to continue our partnership with Amazon Web Services. So we wanted to build this as a cloud native solution, multi-tenant software as a service platform. And we wanted to build an architecture that was fully containerized, completely event driven, and even push beyond the progression that we've all seen going from monoliths to microservices, we wanted to push even past that. So in order to create something that disruptive, it required, in the traditional sense, you have to start somewhere. You don't, and you don't want to rewrite reinvent the wheel, as it were, because when you are trying to innovate, speed to market is very important. So when we started, we looked at various cloud platforms, database platforms, tools for data science, and there's a growing number of those available in the cloud today, even on Amazon. So we started there, and we connected to all these different database platforms that deal with structured data, NoSQL data, time series, key value, all these sorts of things. And we realized that in order to plug all this in, to create all of the connections to all the data sets that we wanted, the real-time streams, and to be able to unify and leverage all of that data, I worked on it personally for 2 or 3 months and decided that, there's got to be a better way. Because not only did we have to have access to all these platforms and disparate data, but we also needed to create all of the APIs. We needed to build all the, normalize the data, build training models, and then we had to figure out ways that we could expose those to API calls for our SaaS platform to then be able to consume. And I quickly realized, and the team did, that this would take way too long. It's just way too hard. And, the infrastructure may be cheap in the cloud, but that doesn't mean that everything is always easy. So after trying all of this and trying to find a better way, you can go to the next slide. So I still think it was somewhat of a maybe even some providence of some sort, but I had never heard of Iguazio, and but I found Iguazio, and I'm really glad I did, because Iguazio offers a data science platform that includes pretty much everything that I was struggling with in terms of time and cost and energy. So first and foremost, it has a multi-model database. So instead of choosing multiple database platforms in the cloud and trying to normalize that and synchronize that, Iguazio offers a singular, easy API for me to access and interact with data in all of the formats that I need to, and I don't have to learn 4 different APIs. So that's very, very awesome. The other thing is, obviously, if you look at the whole MLOps tool chain and the whole pipeline, it all starts with ingesting data. So, if you find the data, you have to be able to ingest it. And normally, in any other situation, you wouldn't have all of these capabilities self-contained in one platform. But the ability here to ingest data, to prepare the data, to train models against the data. And as soon as I have a trained model, Iguazio's data science platform includes a serverless capability called Nucleo. And it allows me to then take that trained model and push that directly using CI/CD, continuous integration, continuous deployment, to production. And what's interesting about the Nucleo serverless functions is these are in keeping with the architecture that we sought in our platform. So everything is containerized, everything can be triggered by multiple sources, and those jobs can also be chained together. And we continue to expand the relationship with Amazon Web Services to produce these pipelines and make them accessible. By leveraging the Iguazio platform, instead of looking downstream and seeing that it was going to take 6 months, 8 months, a year, we were able to achieve production-ready MLOps in weeks, as opposed to the alternative. So the real-time streaming data, batch data, all that sort of stuff is available within this platform, and that really helped us deliver ROI in weeks. Whereas prior to leveraging this platform, it looked like it would probably take us longer than we wanted to get to market.
Hey, Jason, I see one question in the crowd about are you using Amazon Lambda? So can you explain that point? I think you're essentially what is Nucleo and what's the difference? Why you couldn't use Lambda and you use Nucleo?
Yeah, sure. That's a great question. So there's a really big scenario in the way the pipeline operates for us. So it's really related to state.
And maybe just another comment. Nucleo is an open source project, very popular, more than 3,000 GitHub stars. Everyone can use it. It's not confined just to the Iguazio platform. It is developed by Iguazio, but it's open source.
Yeah, absolutely. Well, and having it integrated into the platform though is very easy, provides an easy way for us to deploy those models and utility functions directly in the data science. So we can have database engineers as well as data scientists operate in the same environment. That's very, very helpful. But yeah, so it's really, to me, the difference between Nucleo and Lambda. There are several. One of them is maintaining state. The other one is the ability to control, I would say, the complexity of deployment and the granular execution. To be able to chain those things together is a significant difference between what Nucleo offers and what Lambda offers natively. So we can go to the next slide. So just I don't know how many techies or coders we have out there. This is the very simple example where you can have multiple pipeline components deployed on Nucleo, and each one of those can determine which data sets and which correlations, predictions, whatever it happens to be, matches the input. So we can determine essentially there's not a one-to-one correlation. And here's a piece of data in a typical data query. You would say select some piece of data from some database. This is about understanding what's actually understanding the question and then parsing the question to execute a variety of MLOps pipelines to produce data that correlates or relates to the information that was passed in. So it's essentially leveraging machine learning where you have one small piece of data and have that small piece of data be matched across multiple real-time data streams or historic data streams or information that you've learned from past interactions. The next slide. So some of the takeaways and sort of ongoing focal points, obviously operationalizing MLOps at scale really requires the ability to connect to literally millions of potential data sources, untold number. You can't even measure the number of data points that are engaged in an entire end-to-end business process over time. So it does require sort of a lot of focus on delivering it. And so for us, going from something that we would have to spend literally, I would say, man months, years, we would have to train and hire a whole bunch of experts to build and sew together all of these different systems. By leveraging the abilities that are afforded by the Iguazio platform, we have been able to unify this multi-model database. We have a single API for accessing the data, whether it's from a stream or whether it's from live data sources, etc. We can go from ingest to training to production in hours and days versus weeks and months. And that's a big takeaway because traditionally, there are different people who do different jobs along the MLOps pipeline. having a platform that unifies the expertise across our team, data scientists, developers, that sort of thing, it has really just been amazing. So we talked a little bit about, so it's interesting, about the statefulness of Nucleo and the performance. And we went from, and this is the biggest thing for me, we went from try to success in under a year. That's something that I don't believe we would have been able to do had we tried to build this ourselves. So some of the focal points and ongoing lessons that we have to focus on, obviously, cloud infrastructure is cheaper than physical infrastructure, but it's not free. So we do have to make sure that our functions and our containers and the code that we deploy is as granular as possible, because there's a memory consumption issue. Taking up more memory takes more cost. We also want to continuously reduce the complexity. We would rather have 100 tiny components than 1 or 10 monoliths. Let's put it that way. So we want to keep that very simple. Also, we want to be able to observe the functionality, because sometimes when you do build these small granular components, you believe that this component is probably going to run n number of times per day, etc. And you find out that because we're building a platform that's constantly learning and constantly evolving, you start to see some MLOps pipelines that are running more frequently than others, and you have to constantly be measuring that to ensure that performance isn't encumbered, and that also leads to infrastructure cost. So once you determine and you have that observability, then you can start to measure and scale back or scale up cloud infrastructure as needed. And then we want to evolve iteratively. There are no, as we build this, there are certain times when there are acceleration curves where you can go from an idea to production and everything, everything just works and it advances a platform like ours rapidly. Other times, you start to realize that problems are more difficult than what you thought. And it's ever changing, just like innovation is in technology, just like new innovation and capabilities emerge, new data sets emerge, we have to continuously evolve. That's the one takeaway for me, and that's a big focus, because I believe that there's a huge opportunity going forward in the cognitive science space. I believe that data is going to provide capabilities that we can't even dream about today, and iterating toward that evolution is certainly exciting for us.
So Jason, a couple of points that we discussed in the past. So I guess you guys have like hundreds of functions. I think that essentially, because you're working with so many data sources, all the social networks and all of that. So is that correct? So and you told me also at a certain point that you had a sprint where in 1 week you build like how many functions? Was that?
Yeah, it was like 100 or so in one sprint. And obviously, it's an iterative process. So that doesn't mean that all those functions are complete, right? But we get, just like anybody else in an agile methodology, we get to working code in a sprint, and then we harden it, perfect it. But
so
yeah, our ability.
If you had to go and develop this using traditional methodologies, taking code, editors, Docker build and deploying to production, instrumentation, logging, all of that, how long would it take what you've achieved in 1 week?
Well, I'll say this: my head of data science, obviously he had never heard of Iguazio either, but he shared just the other day that after seeing the number of functions that we were able to put into production, he said that in every other data science position he's had, going from testing, normalization, training to production is typically 6 to 8 months. And with Iguazio, we're able to do it in days. So it's just, I'm happy that he's happy. Let's put it that way.
Yeah. Another thing that I think we talked about is this, again, sort of iterative improvement that I think you had once functions where you notice that they're utilizing too much resources, too much CPU or memory. And then essentially, just because you had all the observability, you had the monitoring of, the invocations, the memory, the CPU, you just figured this out and re-implemented the function, essentially kept the API and just sort of made it much cheaper just by doing that?
Yes, absolutely. And it's an ongoing thing because um, that's another motivator for us to focus on deploying very granular components. And it really helps to keep the cost down, but even a small granular component leveraging Kubernetes or containerized environment, it can scale. So it can scale horizontally, et cetera. But still keeping it small is very, very important. I mean, I also think that making smaller components that do one job and do it really, really well, even knowing that you can chain those things together, it essentially, it's easier to support rapid change, and it's easier to maintain that observability and some of those performance issues to keep costs
I
down.
think at a certain point you even changed languages for some implementation. You wrote it in one language and swapped to a different language just for sake of efficiency or performance.
Absolutely. Yeah, that's the other benefit. Some developers, like especially data scientists, use different languages. And we found that since we can create these Nucleo functions in whatever language our developers or data scientists want, so far for our most complex things, most of the data scientists are using Python, but we do have people who write in other languages as well.
So maybe we'll address some of the questions I see in the chat. So first, I think we covered the notion of Nucleo. Just so a little more details, Nucleo is, again, an open source project. It's really high performance. It's using sort of a high performance runtime engine. So in some cases, it's actually like 100 times faster than Lambda. We're talking about sub-millisecond latencies, and in some cases, hundreds of thousands of transactions per second on a single function core. And then also stateful. So essentially, it can also attach two volumes and mount over, since it's running over Kubernetes, so you can mount it over something called PVCs, mounted file systems and things like that. And also, it has a lot of other interesting attributes and details. It supports many triggers. So the same function, as Jason mentioned, you can write it, that it can be invoked by HTTP, or by Kafka or Kinesis on Amazon, or it could be invoked as a batch job, something that usually serverless doesn't do. So it's a very versatile and high performance tool. So that's on the Nucleo function. Regarding the data, part of a unique aspect on the Iguazio platform, there is something called a multi-model database. So it's essentially a combination of think of it as a key value, time series, SQL, and other engines all under a single engine. So you can access the same data. You can ingest really high performance. You can run SQL. You could pull data, etc., all through the same thing. And what's unique is also that the APIs are standard. It's not that it's using proprietary API. You can actually access the data as if it was a Pandas data frame or SQL data frame, Spark data frame, or SQL API, or about 13 other APIs that are all standard. So it doesn't require changing your application. What other questions we had here? Yeah, so we use there are about 8 different languages supported. So it's quite a bit, I think, across all of the different languages. Some that are not natively supported, is there a way to run them as well? Like C, there is a way to run C, although it's not like officially supported, and other languages, including R and others. So that's regarding the question that I see here. So if there was any other.
There is also a question here, Yaron, about handling that have a common field, but use different names or data types, such as meta.
So I'm not trying to understand the question. but maybe we can get back to it later um, after we do some demo. Jason, did you conclude with your part of the slides?
Yes, I have. Looking
Okay.
forward to any questions after you're done.
Thanks. So what I want to show you now is as a live demo is, Jason is pretty familiar with this concept of working with microservices. One of the key advantages that microservices, and especially serverless functions, they automate the entire workflow from taking some code and essentially deploying it to production with all the instrumentation and logging and canaries and rolling upgrades and all those things that usually are pretty much of a mess. They're all automated for you. So I'm going to show you how we can build a very complicated pipeline. Sarah, do you have a slide for the pipeline slide? Okay. Sarah, do you have the pipeline slide with the?
Yes. Do you see the pipeline slide?
I see a slide with text. There's the one with the. Oh yeah, this one. So what we're going to see is, again, you wouldn't usually envision something like serverless functions doing distributed training, because again, serverless functions are usually stateless. So what we'll see that you can essentially build an entire pipeline with many different steps, with a lot of parallelism, extremely high performance, that covers everything from data ingestion all the way to deployment in production. And I'm going to try and do that all in a few minutes. Okay. So that's part of the solution, and all the components that we're going to see, they're all open source. Essentially, it's using 3 different open source projects in combination. Nucleo, which is a more of a real-time serverless engine. MLRun, which is a server orchestration, end-to-end pipeline orchestration, also open source. And Kubeflow, which is a very popular open source tool for orchestrating machine learning pipelines. Okay, so with that, I'll share my screen. Can you unshare and let me share? Great. So, okay, what I'm demonstrating right now is a notebook, just first to understand this whole concept of functions. Okay, so essentially I can write code in a notebook or in an IDE or inside some of the built-in editors that Nucleo or what other services have. So this is an example of a very simple function. It opens an archive, reads from S3 as an example, and opens it up into the built-in cluster file system we have, and maybe potentially it can analyze, unzip, etc. So I can write this simple function in my notebook, and then I could even document it if I want, add description, give it categories, because maybe I'm going to push it into a marketplace like we're going to see in a minute. And then I could just export that, locally or into a function sort of marketplace or database. And then later on, I can just import that function and even read all the documentation. The documentation is being generated automatically from the documentation of your code. And then I can just go and run those functions locally in my notebook or as a job, distributed job on the cluster. So this is an example of sort of more of a batch function that takes some data, reads from S3, does data preparation, a very simple data preparation, and essentially I can run it locally on my notebook or as a distributed job on the cluster with the same ease. Another type of function is more of a real-time function. So let's look at, this is an example of a serving function. It's what we call Nucleo serving. It's a sort of subclass of Nucleo that does model serving. It's huge amount of code that I need to do for model serving. You see about 20 lines or less. Just loading my model and running the prediction. And again, I can write this function in my notebook and I can just save it. If I want to test it, I can just go and deploy that function and run it again. Very easy to work with functions. I could write them and deploy them. And now let's build a full-blown project that's using a bunch of functions. So again, I could take, this is all, by the way, all the demos that I'm showing, they're all in Git. We can later on send a link into those. So let's build an entire end-to-end pipeline that involves ingestion, analysis, training, validation, building deployment of model serving and other things, all in a single notebook. So The first function is essentially ingestion. I'm just going to read the standard iris data set, very popular data set in data science. So this is a very simple function. It essentially generates the data sets, and then it's logging the data set into the experiment database and artifact database of the cluster. And then I can just go, I create a project. The next thing I'm doing, I'm running my function. One inherent thing into the functions, because the functions are very well defined and they're sort of a sandbox, they automatically record all the inputs and outputs. So everyone is working very hard on experiment tracking. With this technology, experiment tracking is built in already. Data lineage, experiment tracking is built in without doing any extra work. So when I'm running my ingestion function, essentially it automatically tracks this task, and I can see all the metadata around this task. If I want it in a nicer UI form, I can just go and look at my functions and all the artifacts that it generated. So it's all also written into sort of a database. The next thing I want to do, I have a data set now, I want to run analytics and feature extraction and feature analysis on that data set. So I can just, in this case, I don't want to write a function. Again, I'm too lazy. I'm just going to pull a function from the marketplace, which is doing analysis. It's generating, I don't know about all the features that it's using, so I can just check the documentation, what are the parameters, and I'm going to run this function with some parameters, like give it the iris data set as an input. It's going to run. Everything, again, is going to be tracked, and it generated a bunch of data points. Those data points actually came back into my notebook. So let's see what we have here. So this is an example of analysis of all the features. Let's look at the imbalance. Looks pretty cool. Our seekers and etc. All those different artifacts that were generated by those functions can actually, because it's stateful functions and they share file systems and things like that, I can actually see the results of those functions in my notebook. And now let's build an entire pipeline that involves 5 different steps. The first step is classification, essentially distributed training with AutoML built in. Then I'm running a validation step on the same results of the training. Later on, I want to deploy a serving model using a local function. And eventually, I want to do live testing of my function, again, fully automated test to check the performance and latency of my model serving, etc. So again, I don't have to write. In some cases, there are library functions that do everything for me. In some cases, another member of the team can write a function or tune it as Jason described. And now I need to build a pipeline. The pipeline is using Kubeflow technology, again, a very popular open source project initiated by Google. And in this pipeline, this graph computation engine, we put all the functions. We essentially create an ingestion function. By the way, in this, the serving function, another unique thing that it's doing is also creating stream of all the inferencing data, which is later used for drift detection, automatic drift detection. So the first step will be ingestion. The next step is analysis of the data. The third step is to run training with AutoML using 3 different algorithms. Part of the issue with AutoML is that if you let it loose, it's going to consume huge amount of resources. So sometimes you want to confine your AutoML technology to various algorithms that you already know that are going to generate better results. So this way you don't waste too much energy on computation. And this AutoML training function will select the best model by inspecting the accuracy. Once we have the training model, we want to create a validation. So we take out the output of our training and feed it back into the validation with the model. Once we have a validated model, we want to automatically deploy it into a staging environment. So we just use another function. This time, instead of running it, we're telling it deploy this function, as the input for that deployment is going to be the output of our training. So essentially, I'm taking the model, taking it into a function, telling this function, go deploy yourself, is a real-time function that is going to serve the model. And once I've done that, I want to test that my model serving function is actually working and inspect the latency, and the accuracy of the results. So I'm running another function that is essentially going to take the output of the deployment, the address, the endpoint address of the deployed function, and is going to bombard it with a data set of, test data set, and also inspect all the results of that. So this is a pipeline that I defined in like 30 lines of code, essentially an end-to-end machine learning pipeline. The only thing I need to do is just run it. If I'm going to open now Kubeflow, which is part also being managed by our platform, but it's an open source project, then what I just drew in Python, I can see also visually. So you can see that I deployed my function. The next step, I got the data, and I can even see a snapshot of the data that was generated. I'm running training. So the library functions already handle the plotting and all this hard labor stuff, ROC curves, etc. I can see the analysis results of my data sets. And later on, I'll do testing on top of my trained model with a bigger data set for testing, again, fully automated. I'm taking the model into the deployment function. I can check the log. You can see that it's deploying creating the container for the function deploying, and generated an endpoint. And finally, once it's ready, I'm running the live tester to measure the performance and behavior. And you see it's green, meaning it's passed the test. So I'm running a combination of 3 different tools in a single workflow. Essentially, I have CI, which is building containers and deploying stuff. Have something like Airflow, which is data analytics pipeline for data preparation and analysis. And you have a machine learning pipeline, all combined into a single tool. Now, once I have all of that, after it's running, I can also go and inspect all the data and the functions. For example, let's look at the training. We used the AutoML. So let's look at the different experiments that we ran. You see, we ran 3 different experiments using different algorithms, and it automatically chose the logistic regression as the winning experiment because it had the highest accuracy. Again, I didn't have to work hard. I just specified which algorithms I need, and this is all done correctly. If I really want to look at the logs in detail, I can even do those. The next thing I want to see is, you remember I deployed functions. So now I'm going to move to the Nucleo UI. Again, Nucleo is open source, and you could use that also not only on our platform. And you could see that I have 2 serving functions. I have the version 1, which is ready from the previous life, and I have the V2, which I use in my pipeline. And now you see the API gateway is only connected to V1. So what I want to do now is a canary deployment. So let's go to the API and open the API, edit it. Let's add the canary. Okay. This is the V2. Oh, sorry. V2. Okay, maybe it's scaled down to 0. Okay, I added the V2. Let's choose the percentage, save. And now, essentially, I deployed a canary. So I have 2 functions that run together. One of them is getting most of the data. The other one is getting less. If I want, I just change the ruler, and I have this function. By the way, if I want to monitor my function in a standard tool like Grafana, I just open Grafana, and I see CPU utilization, GPU utilization, model drift behavior, etc. Part of the way that it's using, it's monitoring all the behavior of my model, is because those serving functions that we wrote in 20 lines of code, another thing that they do, they also stream all the results of the inferencing, the requests, the responses, the duration of the inferencing, and all the other information. So, and this stream is going to feed into another function that I'm not showing here, which is doing drift detection. It's analyzing the results from all the serving functions, and it will automatically trigger and log the events about drifts into Grafana, into a time series, and that will also generate alerts, so you can retrain your models once you see those events. Okay, so with that, I think we finalized the demo.
So
Okay.
there's a question here about the training, Yaron.
Yeah.
How do you handle the testing goals over time as you train and retrain? Do you have comparisons against an established benchmark for the model or algorithm?
Yeah, you're asking how do we know when to do retrain? Is that the question? I'm not sure.
I imagine that's what they meant, yes.
Um, I think part of it is, again, measuring drift of your model, and there are three ways of measuring the drift or behavior of your model in production. You know, obviously before production, you're just doing a lot of testing and labeling, but when it's in production, there are different ways of detecting that, because sometimes just if you see that the statistics of the data that is going into inferencing is different than the statistics of data that is going into training, even without knowing the exact details of the results of the inferencing, you can already assume that there is a problem of drift, and you should go and check that. So there are different strategies. This is an example of a more statistical strategy. There's another strategy, is essentially this drift, this stream that is generated by the function is automatically generating Parquet files that could later, using Athena or Presto or some of those tools, you can compare those with the actual data and see that what the model was inferring, you know, probably after some delay, once you have the real results, you can see that there is a mismatch between the inference of the results, or the Y tag, and the actual results of what happened in practice. So that's looking into other questions here. Which tool we're using for pipelines? So again, it's Kubeflow. Kubeflow is a popular project led by Google. We're also one of the contributors, and also other big companies, Bloomberg, Azure, etc. I think even Amazon is involved in the project. So it's not Jenkins. It has some of Jenkins functionality, but it's mostly focused on data and machine learning, whereas Jenkins is more for CI. You can actually use some of the things that you do in Jenkins in Kubeflow as well, but it's not Jenkins as is. There's also integration that we're going to show, I think, next month, together with GitHub and Azure. We're going to show a full GitOps. So essentially how we integrate those technologies with GitHub Actions, which is sort of a CI engine in GitHub. That's something that we're going to speak, I think, in a couple of sessions. What else we have there? Which tools for testing? Again, for one of the things that we've done here that you've seen is a lot of pre-baked functions that we have a set of data scientists that are working on, this AutoML functions. All of those functions are open source. You can reach us later to see the code. People can take those functions, modify them, and essentially, or use them as is. They're also one of the great advantages of serverless. You can optimize the containers. So usually when we build those reference functions, we already build like Intel NKL and DAL libraries, or NVIDIA CUDA latest libraries, etc., built into the container. So it sometimes even performs like 5 times faster than if you're just going to build it yourself. And again, all the recipes are all open source and available for people to play with.
Yaron, there's another question here about training for the professionals to build applications. So maybe you want to talk a bit about how we help customers on the Iguazio platform.
Yeah, so in many cases we have groups of services, managed, services and support and customer success. It's a large team that involves data scientists as well as data engineers and others. And we're not trying to build stuff for the customers. This is their own work. If someone wants us to build an entire project, we may involve another company. But our data scientists and data engineers are helping customers in sort of training. Again, they're very expert, very knowledgeable in this space, and they're helping customers with their use case. They review code of the customers. In some cases, they offer optimizations and and a lot of ideas. When we're talking about recipes, it's more function recipes. Okay, it's not like if you look into, as we mentioned before, the way that serverless works. You know, this is a model serving function, so you can see it essentially has a recipe. The recipe involves environment configuration. Like do that if you're going to Nucleo or other engines. And if you go, by the way, into the function in Nucleo, you can actually go and edit the code. But there's also a lot of configuration. And what it does, essentially, every function is essentially sort of a YAML file. So this is a recipe that is pre-baked. It includes all the information about the images that you may need, environment variables, images, even storage volumes that it's going to mount on, etc. This is essentially the recipe. So it's more of a serverless recipe and not like a chef or puppet. Multi-tenancy, yes, it's part of our solution. What other question we have here? And again, all the solution is based on Kubernetes, whether it's your Kubernetes or Kubernetes that we can bring with our platform pre-baked. And then again, Kubernetes supports a lot of security and multi-tenancy, and since you can run any service that you want on the platform. And if I'm going to share when you log into our platform dashboard on the Iguazio system, you could see that you have a catalog of services that are all running on the same cluster. You could see many of those services that I mentioned: Grafana, Managed Jupyter, Kubeflow pipelines, even traditional Hadoop tools like Presto and Spark and Hive. They are all sort of managed services on top of the platform that any other service or function can use those through APIs.
Yaron, another question that's come in through the Q&A is whether we support unsupervised use cases.
Yes, of course. Again, the point is that it's an open platform. It's open that essentially you can code everything you want on it, or in some cases we bring opinions and create sort of those recipes or those functions. And even when we do, we're opening it up because our goal is not to be sort of provide you some closed box that you don't know how it works. Our idea is to try and enable and empower people to do their own work. If they want to take the same function and change it, they'll do so. And if you look at the different demos that we have end-to-end demos that are in a Git that you could see face recognition, document and NLP examples, time series analysis for manufacturing or for other use cases with security-related applications. We also have an application we talked about last week around hospital ICUs for managing sort of corona patient status and health and predicting treatment. So many of those things are open and could be used by any customer.
Thanks, Yaron. And there's a question here for Jason. Have you tried to measure, or do you have a ballpark estimate of your human productivity improvements in terms of costs? And where do you see the biggest cloud cost savings coming in? Is it in reduced memory requirements or better cloud cost stability, consistency? Can you say a couple words about that, Jason?
Certainly, that's a great question. Obviously, I don't think there's a 100% accurate way to measure it, but based on the experience we had on the first part of the question, the experience that we had in trying to sew together a bunch of separate systems and platforms to what we were able to accomplish with Iguazio, I would say we saved man years. That's my take on it. So that's absolutely true. In terms of the cloud infrastructure and cost and optimization, it really does come down to two things. One is memory utilization um, and consistency. Those are the two places where we see the opportunity to reduce infrastructure costs. That's one of the reasons that we chose a very granular architecture, not just in the MLOps pipelines, but even in um, the components that we're building for our SaaS platform. We are, I mean, I think of it as a cell, and I think just like the human body, every cell has a particular job. I want them to do their job. They don't need to worry about anybody else. It's completely distributed, so that really helps to and especially leveraging serverless. It allows infrastructure to scale down when it's not being used, versus you know, having containers that are running all the time. But that's really the things that we watch. You don't want, you know, 50 components that are very granular and then 10 or 20 components that are huge. There's an imbalance, and scaling will automatically cost you more. So that's what we've seen. Does that answer your question?
Yeah, that's great. Thank you, Jason.
Sarah, maybe we want to also mention that I think the next episode we're going to specifically talk about the drift detection and automation and sort of retraining and all that based on drift. And one of the presenters will be our lead data scientist that is working on that.
Yes, that's a great point, Yaron. So I'll just go back to my presentation for a second. We have a few more minutes.
And there was another question around deployment of Iguazio. So Iguazio could be deployed either on cloud, we're partnering with the different cloud providers, or on-prem. And we're also partnering with the different infrastructure vendors, or you can deploy it yourself. So you could deploy it through Dell, NetApp, Samsung SDS, NVIDIA, or others, or talk to us directly.
And maybe we'll just take one last question about facial recognition and computer vision use cases.
So there is actually two very nice demos that we have on our demo repository. One is around image classification. Again, similar to the way I showed it, a full-blown pipeline anywhere from image labeling, training using distributed TensorFlow and Keras and Horovod, and using real-time serving of image inferencing. There's another demo that is end-to-end face recognition, all the way from capturing of the images. You know, there's a small app that captures images from cameras, doing retraining every time there's new images, doing image labeling. So there's an end-to-end demo. We can, you know, ping us, and we can return back to you later with the links to the repos.
Great. So we are nearing the end of our time, and just wanted to say that we do have a lot of collaterals about MLOps, and we invite you to learn more about this topic on our website. We have videos of industry experts from Netflix, the New York Times, Uber, and many others presenting their insights and best practices on MLOps. We also have blogs on this topic and other assets, so you just need to log on to iguazio.com/MLOps. And like Yaron mentioned earlier, we'd love to have you join our next session. It's going to be a great one with Microsoft and Git, and it's going to be all about concept drift. And that will be happening next month. We will send an email with the dates and everything else. Please do let us know if there's anything specific that you'd like to hear about. You can email us at info@iguazio.com. And if you want to hear more about Quadient, please email them at info@quadientdxp.com. Thank you very much, Yaron. Thank you very much, Jason, for the great presentations. And thank you all for being here with us today.
Thanks, everyone, for showing.
Thank you.
Bye, everyone. Thanks.